So let's get started. A few announcements here, all the arrangements for next week. And then yeah, for this afternoon, if you have any missing labs, you can come in and make up your missing lab. Okay. Also for you guys online, you are attending Wednesday's lab, you can still come in if that's available to you. So next week, we will have our exam too. So Friday lab attendees will take exam on Monday, and then Wednesday, folks will take the exam on Wednesday. Okay. So because we have exam on 2 days, so then there will be a asynchronous lecture for next week. Okay. So for Wednesday, folks, on Monday, you guys want to watch the video or lecture video. And then for Friday, folks, you can watch it on Wednesday. Okay. So and then on next Friday, we will all meet online because Friday, folks, you already coming in on Monday for the exam, so you don't have to come for the lecture. Okay. So we'll meet all online. Okay. That's the arrangement for the lecture next week, and then the lab will still meet as scheduled for next week. Okay. So all right. So let's take a quick look on what we learned last time. So we learned the definition for work, which is equal to force times displacement if they are in the same direction. Okay. And the SI unit for work is joules or meters times newtons. If the force and displacement they are not in the same direction, then you take the angle between them and then do F times D times cosine. Okay, so the magnitude of the force and then distance traveled times the cosine, the angle between the two. All right, and then if there's multiple forces on the object, you can figure out the network on the object either way. One way is to figure out the net force first and then do the net force times d times cosine theta. Or you can figure out each work done by each force individually, then you can add them up, okay, to the net as the net work on the system. All right. And later on, we check on kinetic energy and work energy theorem. So basically, if you have work done on the object, okay, and if the force and the displacement are in the same direction, so that means you have positive work done. Okay, so if you have positive work on the object, then the velocity of the object or the speed of the object will increase. Okay, and then if otherwise, if negative work is done on the object, then the speed will decrease. Okay, so it's also represent in the work energy theorem where it said if you have net work or if you have total work on the object, then it's equal to the change in the object's kinetic energy, which kinetic energy is defined as 1/2 mv square. Okay, so that's related to the speed. And we also talk about work done by varying forces. Okay, so in general, you can have the force, its components, in the displacement direction, versus displacement plus. So then you can make that graph. So then whatever the work done on the object should be equal to the curve underneath, or the area underneath the curve. Okay. That applies to both the constant force and then varying force cases. For special force of spring force, which F equal to Kx, then work done from say one position to another position, from initial 0 to another position final, is equal to the area again underneath the curve of force versus position. In this case, because force is equal to Kx, so then work done is 1/2 Kx squared. Okay, it's the area of that rectangle there. All right. So today we are going to check on new sections here. We will talk about two types of forces. One type is called conservative force. The other is called non-conservative force. Okay. So for the definition of conservative force, if you are doing work against that force, all right, if you are exerting a force on the object and then the force you are exerting is doing work against the conservative force. So for example, if you are moving a box from the floor to a certain height, okay, so then the force you exert on the box is against the gravity, right? So you are doing work on the up box. Now, if you release your force, then the object will gain kinetic energy or will gain speed, okay? So then that force you are doing work against is called conservative force, okay? So in this case, gravity is a conservative force, all right? And otherwise, if you are doing work against the force, okay, so for example, if you are pushing an object across the floor or table here, if you are pushing this guy over there, okay, so then you are doing your work against the friction force, okay. Now, if you release your force that is against the friction force, then the object will remain stationary, okay. So it will not gain kinetic energy or the speed will not increase in that case. So then that force you are doing work against is called the non-conservative force, which is friction, okay. So these are two examples, one for each type of force. Now, conservative forces in this method particularly, most likely you are going to just see two forces as conservative forces, okay? So one is gravitational force. The other one will be the spring force, okay? The force by a spring. So those should be just the only two forces that are considered conservative force this semester, okay? Now next semester, when you learn about electric force, then that's another another conservative force, okay? Other forces are most likely non-conservative forces, okay? So for conservative force, if you are if work done by that conservative force is along a closed path, then the work done should be zero. Okay, so in the figure shown here, so if you have box, it's moving on this vertical plane here. So from point A, B, C, D back to A. So then the work done by the gravity, the conservative force, okay, you can add them up. So in this, from point A to B, because the displacement and then the force are perpendicular to each other, so the work done should be zero. In this case here, displacement is upward, force is downward, so then this will do negative work, so minus mg times the distance, which is h, okay? On the top here from C to D, again, force and then displacement are perpendicular to each other, so then work is zero. But from D back to A, force and displacement are in the same direction, so it's mgh positive, okay? So if you add up the work done during these four parts of the motion, you will figure out then the work will add up to be zero, okay? 0 plus a negative mgh and a positive mgh, that will add up to be zero, okay? So work done by a closed path of a conservative force is zero. So it doesn't have to be a square form. If this is a circle, then it's still going to be zero. It's a rectangle, it's going to be zero, okay? As long as it's a closed path, then it's going to be zero, okay? On the other hand, if you have a non-conservative force, for example, if you are looking at the friction force, okay? So this time, let's imagine you are looking from a top view here. So this is a horizontal plane. If you have a box, then if the box is moving from A to B, C, D back to A, okay? So you can see that because friction force is always against the relative motion or the motion of the object, so then the force and then displacement, they are always in the opposite direction, okay? So then work done is always negative of that force, which is mu k times m, and is equal to mg times d, okay? So then friction force times d, a negative sign. So on this one, it's the same scenario here. Force and displacement are opposite to each other. So negative here, negative here, negative there, okay? So if you add the work up for this closed path, then it's going to be a non-zero number, right? It's going to be a negative number in this case, okay? So for a non-conservative force, the work done on a closed path is not zero, okay? Now, if we look back at the conservative force, so you can start from point A, right? Moving an object through this path, red path here, go to point B. Now from B back to A, you can have two options. You can go from this purple path here. You can take the green path here, okay? And then go back to A, all right? Now, because work done by a conservative force on a closed path is going to be zero, so you can see that work done on this part, red part here, W1 plus this purple part, W2, right? It should be zero because object goes back to the original point, right? So that's a closed path. Now, if you examine it, another scenario, again, from A to B, and then from B, now this time take the green path over here, right? Now you go back to point A. So it's also a closed path. So then W1 plus W3 should also equal to 0, all right? So you have W1 plus W2 equal to 0. You also have W1 plus W3 equal to 0. So that tells you W2 and W3 should equal to each other, okay? So then that shows you that you are taking the path from point B to A, or you are taking this green path from B back to A, then the work done by the conservative force is the same, right? So it doesn't depend on the path. If their starting point and then final point are the same, then the work done by the same force should be the same, okay? So for non-conservative force, it's again, or it's path independent, and then it's also zero on any closed path, okay, for the work done, okay. So those are the two characters for work done by a conservative force, okay. On the other hand, if you have a non-conservative path, then it's path dependent. It's also non-zero on any closed path, okay. All right. So then let's take a closer look on the gravity. Okay, so if you are doing work against gravity here, then what happens? Okay, so if you are, like, say, doing work against gravity, so you can move a heavy television through the going upstairs, or you can design a simple machine like this. You can pull it up and then put it into the say third floor or whatever, fourth floor. Okay, so you can do this either way. So, but you realize if you are doing work against the television going upward, right? So then, if say whatever reason happens, if you end up to be throwing out the television through the window, or the rope breaks at some point, okay, so you'll realize that the television is going to gain a lot of speed, right, throughout when it goes down, right? And that means there's something converting to its kinetic energy, right? If that happens. So when you are doing work against gravity in this case, then you are actually store energy into the system, into the television here, okay? So that energy, we call it potential energy or gravitational potential energy, because you are storing energy by doing work against the gravitational force here, okay? So for gravitational potential energy, we can call it potential energy or PE, or sometimes you see people use U as the symbol, okay? So, so if you are doing work against the gravity, then you actually increase the object's potential energy, right? So then work by the force you are doing against, work against the gravity is equal to change in potential energy, okay? So that's equal to this guy. But if you are doing work against the conservative force, so then work done by the conservative force should be equal to negative of this guy, right? Because this is the work you are doing against the gravity. So then work done by gravity should be negative of it, right? Okay. So in that sense, work done by the gravity or conservative force here, so it's equal to um, initial potential energy minus final potential energy. Okay, so I think for up to this point, when we talk about a change in certain quantity, we use the final minus initial. Okay, but this guy is just work done by conservative force. Okay, so it should be equal to initial potential energy minus final potential energy. Okay, so that's something you might want to make a note. Okay, or if you use U as the symbol for potential energy, then it's U initial minus U final. Okay. So for potential energy, because it's another form of energy, so it should have the same SI unit as energy, which is joule, or kinetic energy, which is joule. Okay. So work done by a conservative force then actually reduces system potential energy, right? Because if you look in this way, if the television goes down, all right, then its potential energy is being converted to kinetic energy. So the potential energy reduces, but kinetic energy increase. Okay. So work done by the conservative force will reduce the system's potential energy. Okay. However, if you are doing work against the conservative force, then you increase the system's potential energy. Okay. So when you are dealing with gravitational potential energy, okay, you want to pick a reference point, okay, where you can define as your reference gravitational potential energy level, or you can simply set that to be 0. Okay, so this is similar to your choice of the origin of a coordinate system. It could be arbitrary. Okay, so you can pick any point to be your gravitational potential energy ground level. Okay, so if that is set, okay, then that's your y equal to 0. Okay, so then gravitational potential energy will be just equal to mg times y. Okay, if you want to use u as the symbol, then it's u equal to mgy. Okay, all right. So we'll take a look on one example on the gravitational potential energy here. Okay, so in this case, it says a 0.33 kilogram pendulum bob is attached to a string 1.2 meters long. What's the change in the gravitational potential energy of the system as the bob swings from point A to B? Okay, so in this case, you can ignore the string here. It should be a massless string unless otherwise stated. So then you are pretty much just focused on the pendulum bob here, the ball here, okay, from point A to B. So try to see if you can figure out its potential gravitational potential energy difference, okay? So you'll have to pick up a point where your gravitational potential energy you set to be 0, okay? So then that's your y0. Then you are looking for mgy final minus mgy initial because gravitational potential energy is mgy, okay? All right. So let's take a look. You guys can keep submitting your responses, but we can take a look here together. Um, so the ball goes from A to B, or the pendulum bob goes from point A to B. Okay. So here is where the position of B, Y of B, and then here should be Y of A, the level for Y of A. Okay. So you want to pick up a ground potential energy level or ground level potential energy. So usually it would be most convenient that you take the lowest point of the motion for the object to be your ground level. Okay, so in this case, the lowest point will be at point B. So that's your ground level potential energy. Okay, or U equal to or P equal to 0. Okay, if you prefer P as potential energy. Okay. So that's your potential energy equal to 0. Then that's where your Y is going to be 0. Okay. Um, so in this case, then your YB is equal to 0. Okay. Then your YA is equal to this part of it, right? From here to here. Okay. So this part of it will be equal to the total length of the string, right? Minus this part above it, above this level. Okay. So this part, if you look at this triangle here, it's a right angle triangle here. So this is the hypotenuse. Then this guy, adjacent to this angle should be cosine of the hypotenuse. So L cosine, okay? So your YA then will be L minus L cosine theta. Oh, let me write it over here. YA is equal to L minus L cosine theta, where L is equal to 1.2, theta is 35 degrees, okay? So your YB will be 0. Now you're looking for your potential energy change, either delta U or delta PE. All right, let me just use delta U here. So that means final minus initial, okay? So final is at B, initial is at A, and then potential energy should be equal to mgy, okay? So then this would be mg YB minus mg YA, okay? So YB is 0, so then this guy is 0 here. So be negative mgya, negative mgya, which is this guy here. So it will be L minus L cosine theta. Okay. So that's your delta U. And then I think you have everything you needed here. So M is 0.33, G is 9.8, L is 1.2 minus 1.2 meters cosine of 35 degrees. Okay. So that should give you negative of 0.70 joules. Okay. So the sign should be negative because your final is at lower point, right? Than your initial. So then final should have a lower potential energy than initial. So the change should be negative. Okay. Okay. So y is ya equal to L minus L cosine theta. So that's because ya should be this part, right? Ya. This is the 0. So then ya should be this length, right? Over here. So then this length is equal to, this is L, right? From the hanging point, that's L. Yeah, right. Yes. Okay. All right. Now, as I mentioned earlier, for ground potential or ground level potential energy level, it's arbitrary. So you can try to pick this as your ground level, okay? So you can pick this as your ground level. You can do this after class, okay? And then you can give it a try. So then in this case, if you pick that as your U equal to 0, then your YB should be equal to minus L because this is 0, then B position of like vertical position of B should be minus L. And then your YA should be equal to just L cosine, minus L cosine, okay? you can try to do the same thing. It will turn out that the change in potential energy is going to be the same. Okay, so if you do that, you'll figure that why this is arbitrary, could be arbitrary. Okay, but as what we did earlier, when we pick a origin for the coordinate system, you stick to it. Okay, you don't change the ground level while you are solving your problem. Okay, just once it's picked, you fix with that one and then stick to it. Okay. All right. Any questions? You guys might still have. And then again, as I mentioned, often it's most convenient to choose a low point to be the ground level of gravitational potential energy. Okay. All right. If not, then we will take a look on work done by a couple of the conservative force. Okay. So for spring force, which spring is also the force by the spring is also a conservative force. Okay. So if you let me see. If you are doing work against the spring, so for example, if you are pulling the spring, or if you are pressing the spring, okay, so then you are doing work against the spring or the spring force. Then once you release your force, then the spring will gain speed, right? You'll bounce back to where its original position, and then probably doing a few oscillations before you come to rest. But in that sense, you can see you are doing work against the spring force, then the spring force, the spring will gain kinetic energy after you remove your force. So then spring force is also a conservative force, okay? Work done by spring is equal to 1/2 kx squared, okay? So we checked this earlier when we check on the work done by a spring, okay? So that should be equal to potential energy for a spring, initial minus potential energy of the spring final, okay? And then for potential energy of the spring, it's also, it's called elastic potential energy, okay? So two types of potential energy, gravitational potential energy, and then this one is elastic potential energy, okay? All right, now usually for elastic potential energy or the potential energy by a spring, we usually take the natural length of the spring, that to be the reference point where the potential energy or the elastic potential energy is 0, okay? So then potential energy by the spring is simply 1/2 kx squared, okay? The same expression as the work done by the spring, okay? Now it doesn't matter because the x, you actually do the square to the x, okay? So then there should be no minus sign there. So on that, we will take a look on this guy here, this example here, where it says the work required to stretch a certain spring from an elongation of 4 meters to 5 meters is 30.5 joules. What's the work required to increase the elongation of the spring from 5 centimeter to 6 centimeter? So work done equals to potential energy change. Okay, I'm going to use PE here this time. Okay, so it could be either way. It could be E, it could be PE. Okay, PE final minus PE initial. And then because this is a spring, so PE potential energy is equal to 1/2 kx squared. Okay. X would be the elongation of the spring in this case, or compression of the spring in if this is a compression. But in this case, you are stretching the spring. All right, I think let's take a look here together. Okay, so it may take quite some time for you guys to figure this out. But um, so it tells us work done, or let's take this. So it says if you are stretching the spring from 4 centimeter to 5 centimeter, okay. So work is equal to, so then let me, I'm going to call this as work one, okay. 30.5 joules. And if you are stretching it from here to there, so then work should be equal to final minus initial. So this is final, this is initial, right? So 1/2 K of final square, so 5.0 square minus 1/2 K initial elongation square, okay? It's asking you if you are now stretching it from 5 centimeter to 6 centimeter, what will be the work? Okay, so let's call this W2. All right. Now you probably can figure that work done should be equal to 1/2 again K. This time you are going from, this is the final. So this is the final, this is the initial this time. Minus 1/2 K initial elongation. Okay. So you have basically two equations. You have this equation and you have this equation. Okay. And then this is 30.5. So this is 30.5 joules. Okay. So in the two equation, you'll see that K is the unknown and then W2 the unknown. So basically from these two equations, you should be able to solve for both K and W2, right? So you can go from the first equation here, you can solve for your K, all right? Which you probably should be able to do it, right? Because it's just 1/2 K, the 5 square, which is 25, minus 4 square, which is 16, right? So 1/2 25K, 1/2 16K, all right? You can do the difference and then figure out what's the multiplier for the K and then divide 30.5 by that, okay? So I'm not going to go in details there, but you will figure out that K is equal to 6.778 joules centimeter square, okay? So once you have that, you can replace the K with the number you figure out, then you can solve your W2, okay? You can calculate for your W2, which would be 37.3 joules. Okay, again, I will not go through details of algebra there, but you guys can do that, okay? I'm going to tell you that how I actually did this one, okay? So I look at these two equations. I look at the first equation, 30.5 joules equals to 1/2 K of 5.00 centimeter square minus 1/2 K 4.00 centimeter square, okay? And then I look at the second equation here, W2 equal to 1/2 K 6.00 centimeter square minus 1/2 K 5.00 centimeter square, okay? I have these two equations, all right? I can look at the right-hand side of this one. So this is 1/2 25 minus 16, right? Which is 9. If you do 25 minus 16 gives you 9. So 9 over 1/2 or 9 over 2. So 9/2 centimeter square times K, okay? And then this guy on this side, on the right-hand side should be also, now this is 36, right? 6 square 36 and then 25 from the 5 square. So then that 36 minus that gives you 11. So 11 over 2, okay? Centimeter square times K. So this is from the right-hand side of the equation should be equal to the left-hand side, right? So let me put the line there, equals to 30.5 joules. And then this equal to should be also equal to its left-hand side, so W2. So I'm looking at this two equations here, all right? So then I can do the ratios of this side over that side, right? So I can do 11 over 2 centimeter square times K over 9 over 2 centimeter square over K, right? That should equal to this over that, right? W2 over 30.5, okay? So, oops, there you go. So I did this guy over this guy, it should be equal to this guy over that guy, okay? So that over that is equal to this over that. So you can see K and K will cancel out, okay? Even the half and half will cancel out, the unit will cancel out as well. So then it's 11 over 9 equals to W2 over 30.5, okay? So basically W2 then is equal to 30.5 times 11 over 9. That's in joules. So that gives you 37.3 joules, okay? So that's another way of solving this, okay? So you don't have to calculate for K if you do it this way, okay? But either way, it should be fine, as long as it works out for you, okay? Questions you guys might have? All right. So if not, then we'll take a look on the conservation of mechanical energy. Okay. So for mechanical energy, it includes both potential energy and kinetic energy. Okay. So that's what mechanical energy means. It's the combination of potential energy and kinetic energy. Um, so we are going to start from work energy theorem we learned earlier. Okay, so for work energy theorem, it says the total work done on the object or on the system, if there's multiple objects, that is equal to the system's kinetic energy minus its initial kinetic energy. Okay, now if you only have one single force on the system, okay, so for example, for a free fall problem, then the only single force is gravity, which is conservative force. Okay, so and the single force happens to be the conservative force. Then the total work done is just equal to the work done by the conservative force. Okay, W sub C, that means work done by conservative force. So then work done by conservative force we learned earlier is equal to potential energy initial minus potential energy final, or the minus of the change in potential energy. Okay, minus delta U. So then you can replace WC in this equation, or W total in this equation, with WC, okay? Because the only force is the conservative force, okay? So then work done is by the conservative force. So WC then equals to KF minus KI, and WC is equal to this, okay, minus of UF minus UI. So then KF minus KI is equal to WC, all right? UF minus UI, or if you put the final quantities to one side of the equation, so that means move UF to one side of the equation, negative becomes positive, and then move this initial quantity to the other side of the equation to be with the initial potential energy, okay? So minus becomes positive, and then for the UI, it's minus of minus, so it's positive. So you end up with kinetic energy final plus potential energy final equals to kinetic energy initial plus potential energy initial, okay? So then in this sense, it tells you if the work done is just by the conservative force, okay, or if there's just one single force, which happens to be the conservative force for the system, then its kinetic energy and final energy final should be equal to kinetic energy plus potential energy final. So that means kinetic energy plus potential energy is constant. It doesn't change, right? Because final is equal to initial, okay? And then also, as I mentioned, so if there's multiple force, but if you can figure that the work done is only by the conservative force, okay? So sometimes the other work may be doing zero, or the other force may be doing zero work, or maybe there's a couple of forces they are doing work that which cancel out each other. The remaining work is just done by the conservative force. Then you can analyze the scenario again. It should be the same result here, okay? So so if you have potential energy and kinetic energy add up to be constant, okay? So if you add up the two, it's called mechanical energy. So then mechanical energy final is equal to mechanical energy initial. Or you can say mechanical energy is equal to constant, okay? And then that's the conservation of mechanical energy. All right. So we are going to take a look on this one. I think we are going to take on look on this one together, because we have only a few minutes remaining here for the class, okay? So this one says, at an amusement park, a swimmer uses a slide to enter the main pool. And it says if the swimmer starts at rest, what's her velocity or what's her speed at the bottom of the slide when she descends through a vertical height of 2.1 meters. All right, so let me sketch. So the slide, it probably looks like something like this. Okay, it's not going to be a vertical slide, all right, but it should have a certain slope. And then this is the where the level of the main pool with the water here. Okay, so if she slides down here, okay. Now, in order to figure out the work on the object, in this case, the body, okay, here, you want to draw the free body diagram as usual, okay? So there's mg here, that will be normal force, okay? It says no friction, right? So then there will be two forces at all the time as she slides down. We can take a look on another instant when she's somewhere here, okay? If she's somewhere here, then the gravity, the weight is still there. Now the normal force is probably in that direction, right? um, so for the normal force, it's always perpendicular, or it's always along the normal direction of the surface in contact, right? So that means when she's over here, the velocity is probably going to be in that direction, and then these two should be perpendicular to each other. When she's over here, the velocity is going to be along the direction of the surface. This is perpendicular to that, okay? So you can see that normal force is always perpendicular to the direction of velocity or the movement of the object, right? Or the displacement of the object at that given instance. So then work done by normal force should be always zero because normal force and displacement, they are perpendicular to each other. Okay, so this is one thing you guys probably want to take a note here. So when you see normal force, then work done by normal force is going to be zero. Okay. So then in that sense, you can see then the total work done on the body should be just equal to the work done by gravity, or let me put W sub G as gravitational work. Okay. So if that's the case, then conservation of mechanical energy should apply here because work done is just by the gravity, okay, or the conservative force. All right, so then you can apply energy conservation over here, which says initial U plus initial K should be equal to final U plus final K, okay? So now again, we have gravitational potential energy involved here, so we can define a ground level. So as she slides down, this is the low point at the bottom of slide. So I'm going to define that as the ground level potential energy, okay? Or U final should be zero. That's the ground level. That means it's the ground level. The kinetic energy of her is 1/2 mv final square, okay? And then initially, the kinetic energy should be equal to 1/2 m initial square, which initial is at rest. So then that's zero. So Ki is equal to zero. Now Ui should be equal to mgy, right? So it says she slides down a distance of, or vertical height of 2.31. So then that's Y initial, okay? So Y initial is 2.31 meters. All right. So when you apply conservation of energy, you write this equation over here. Then you figure out each of these terms in the equation individually by writing out their expressions, okay? Then you can plug in the expressions inside back into this equation over here, okay? So then this guy is mgy, mgyi, if you want. So mgyi plus ki, that's 0, equals to U final is 0 plus K final, or K final, I should say K final here, okay? So it's 1/2 mv final square, okay? Now it's asking you to solve for the final, her final speed, V, So that means you are looking for V final. Okay. So from here, you can see then MGYI should be equal to 1/2 MV final score, right? So you probably realize that you can cancel out the M because on both sides of the equation, the two terms have each has M in there. Okay. So then look for V final, you multiply both sides by 2, okay, to get rid of the 1/2. Then this is V final score. So square root of 2 times G times YI is equal to your final speed, right? So 2 times 9.8 times 2.31 meters, that should be equal to, or square root of it, should be equal to your V final. And my calculation says this is 6.73 meters per second, okay, to be my final speed at the bottom of the slide. All right. Questions you guys might have? Okay. So if not, we will stop here for today, okay? And then next week, you guys will take your exam too. So it's from chapter 4 through 6 from the textbook, or the content covered in homework 4 through 6. Okay. Again, your guide will be just to make sure you can solve the problems in your homework assignments without referring to your solutions. Okay. If you can do that by yourself, you should be ready to go for the exam.